In this lesson, we're going to learn about something called enthalpy. Before we can get into enthalpy, though, we need to talk about how we quantify heat, how we actually account for the amounts of heat. As a reminder, heat, of course, is the transfer of energy, whether it goes from the system to the surroundings or from the surroundings to your system. The symbols here, we'll definitely see the lowercase q, but every so often you might see a capital Q. They effectively mean the same thing. And the units are listed here as joules or calories. Joules is the SI unit, so we'll see that one much more frequently as Joules with capital J. Every so often, though, calories, which you may have heard of before, calories, CAL, with the abbreviation there, is used from time to time too. We probably won't see it as much, but just in case you see that, this is a conversion factor that you can use to help you relate those two. So 4.184 joules is equal to 1 calorie. That number, coincidentally enough, is actually one that shows up somewhat frequently as well. But again, the main thing you want to recognize here is that the quantity that's being measured here is heat or energy that's being moved. That's the quantity. Your symbols are Q, and the units are joules. Side note here, food calories, which you may hear of, like certain packs of food might have like 140 calories per serving. That'll be listed actually as kilocals, which is you see right here, the K in front, or capital C as calories. So really, they actually have a lot more in that sense of what the word calorie means. And of course, the last bit here, the sign of Q is informative, and it's important that you keep track of these too, where if Q is negative, that means heat has been lost by something, whatever it is, right? In this case, we usually look at our system. So Q is going to be negative, meaning heat goes away. And if Q is positive, that means heat has been transferred into whatever object you're looking at. So let's go and break this down into an example where you take a hot piece of metal, which you see kind of here on the left side is a bit of an example there, has been placed into a glass of cold water, and we need to study the change that happens with the metal. All right, so what's our system, and then what's our surroundings? So the most important part of this is that our system, we have to identify what is it we're trying to analyze. What is the part, or the element here that is most important to us? And it turns out to be this hot piece of metal. So our system is the hot metal, or just you can say the metal. What's the relevant surroundings? Now, remember, the word surroundings refers to anything outside of the system, so that can be anything, but the most relevant one would be the water itself. All right, so the system is going to be your metal, the surroundings is the water. From where into what does the heat flow? So that goes, as you can imagine, where high to low energy transfer is typically what you expect. And so the hot metal, right, the metal would then give up heat to go into the surroundings. For the system, what's the sign of Q? Well, we discussed that when Q, again right here, this Q for the system, which is our metal, when energy is departing or leaving the system or leaving your object, that makes it a negative value. So the sign of Q would end up being negative for this piece of metal. And then for the surroundings, the sign of Q would be positive because the water around it that's going to increase in temperature is going to gain the energy that the metal gave off. So that will be a positive value for Q of the water. Let's go and introduce this new term called specific heat. Now, the specific heat, unfortunately, this is one of those terms where it starts to kind of conflate what the word heat means, and it's a little confusing at first. But I think it's important for you to just recognize that you sort of have to categorize this separately. So the word specific heat capacity is the technical term. More often than not, it's just simplified as specific heat, and that's what we'll be using in terms of referencing this concept. But specific heat capacity, or just specific heat, is the amount of energy required to increase 1 gram of a sample by 1 degree Celsius. Now, what we do here is you notice that when we specify 1 gram and 1 degree Celsius, that basically we're giving an even comparison. So if you look on the right side here, I have a chart. The chart here has some substances, and then you have the specific heat capacities listed there. So let's say I want to compare different things, right? Let's say I want to compare, for example, aluminum and iron right there. Well, aluminum and iron, they're two different substances, right? So what we want to do is kind of get an even comparison by saying, okay, I want to just use 1 gram of aluminum and 1 gram of iron to kind of give a good baseline, and I want to see how much energy it takes to increase them by 1 degree Celsius. So that's the definition of the specific heat capacity. And you see on the right side here, there's some values listed. All right, so you see there, this is 0.89 for aluminum, 0.45 for iron. And that basically just says that it takes 0.89 joules to increase aluminum by 1 degree Celsius when there is 1 gram of aluminum. Same thing for iron. 0.45 joules of energy required to increase the temperature of 1 gram of iron by 1 degree Celsius. couple of other details here, going back to the bullet points. It's effectively the resistance to change in temperature, and this is a little bit harder to sort of visualize. But if you look up again back to the right side here, I have aluminum and iron, right, 0.89 and 0.45. What it's saying is that it takes that much more energy, almost twice as much energy, to increase the temperature of aluminum as it does to increase the temperature of iron. So in that sense, it's kind of like you're saying, well, it's a little bit more resistant to temperature changes, right? It takes a lot more energy for the temperature to change in aluminum than in iron. Hence, it's more resistant. So that's something you can use to sort of help gauge this value. What exactly does the value mean? It more or less means the resistance to temperature change. If you look at the other part of this, the other bullet points, anyway, the symbol, a lot of times we'll just simplify to just be C. More specifically, you might see a CS or a CP. Again, I'm providing these just because it might show up. I don't know what sometimes the sources of information will get for various things to reference specific heat. So more often than not, just using C is good enough for this class. And then units here at the bottom is joules per gram dot Celsius. Altogether, all of it is the units, joules per grams dot Celsius. So I want to compare liquid water and solid iron over here to the right side. So let me highlight those, looking at liquid water here and iron here. And, based on some experience just from your own life, I'm sure you can answer these questions fairly easily, and it definitely matches intuition. So number one, which substance requires more energy to increase temperature, assuming the samples have the same mass? And that word same mass got left off, but you get the idea. Same mass. Well, again, looking at the values here, 4.18. 0.45. This actually ends up being where, again, it takes 4.18 joules of energy to increase 1 gram of water by 1 degree Celsius versus aluminum, which is only 0.45. Yeah, water is going to require a lot more energy to increase the temperature. So which substance is more resistant to warming? So that means which substance, when you apply energy, is not going to change temperature as much. It's going to be water, right? Once again, because the specific heat is so much higher. On the other hand, right, iron, which is so much lower, that, as you can imagine, doesn't really take a whole lot of energy for it to change temperature. You can definitely sense changes in temperature in iron much more quickly than you would in water. Going the other way, though, which substance is more resistant to cooling? Well, it's kind of a weird one because more often than not, we usually think of this as like a warming process, where how much energy does it take to increase the temperature. But at the same time, we can decrease the temperature too. How do you lower the temperature of something? Well, energy has to leave, right? Energy has to go away. So once again, what temperature, what energy does it take for a substance to decrease by 1 degree Celsius? Well, it takes 4.18 joules of energy of water for it to decrease in temperature, whereas iron takes 0.45 joules of energy to decrease by 1 degree Celsius. And so, as you can tell, once more, iron is the more resistant substance to temperature changes, regardless of cooling or warming. These illustrations here, I'm actually going to show you one or two things in class if I haven't done so already. So you can kind of take a moment and think about these, how exactly we can kind of visualize specific heat, especially the bottom two. That one makes a little bit more sense, but we'll get to those in class. How we quantify heat. All right, so this is now where we get to use the formulas to actually give values to heat. The amount of energy that's absorbed or released by a substance is a product of 3 factors. And you can see the formula here is Q equals M times C times delta T. So Q is what we've already discussed before. That's the energy that is being transferred in or out of a substance. That's in units of joules, right? So that's Q. That's the first part there. That's equal to M, which is the mass of your substance. That's in grams. C, which is that specific heat we just learned about, joules per grams degrees Celsius, all of that together. And then delta T is the temperature change, degrees Celsius. One thing I want to specify though, delta T, right? Anytime you see a delta anything, that refers to a change in something, so change in temperature, but it's important to also recognize that's always final minus initial. The change always has the final minus initial, always and forever. So in this context, again, this is how you quantify Q in terms of how you actually see how much energy is given up. Now, remember, this is about the amount of energy that's moved, right? So we need to know that this is only a result of a very specific amount of energy that either goes in or out of a substance. Let's see some examples of how this works. Number one, a 10 gram sample of liquid water warms from 45.0 degrees Celsius to 60.0 degrees Celsius. What is the amount of energy absorbed by the water? So let's kind of break this down, right? We're talking about the amount of energy absorbed by something. So we need to think about using Q, right? Q is the amount of energy that's being transferred, whether it be in or out. In this case, it's in. So let's go and set up the formula. We know it's going to be Q is equal to MC, and then you have the delta T. By the way, before I go any further, a great way to sort of memorize this is to think of Q equals MC delta T. It kind of looks like MCAT, MCAT, MCAT. Some of you might recognize as like the medical college admissions test, the MCAT. So a lot of times I'll refer to this as just Q equals MCAT, even though the A is really just a delta symbol. So let's look at what we're given and then how we can apply the numbers here. So we are given the mass delta T, right? We're given a before and an after temperature here, so we actually have a delta T available. C though, well, remember, what is C? That's the specific heat of water, and the specific heat of water was listed before, and I'll talk to you how to use that. So that's a constant that you can always have available, so at least for water anyway. So we have those three, and then we can very easily solve for that Q right there on the left. So that's going to be a pretty straightforward use. Let's go and plug some numbers in. So as you can see here, I went ahead and plugged the numbers in. Let me go and make sure we're clear about some things. The 10.0 grams, of course, make sure you have the 10.0. That's the original number. The value for specific heat of water is a little bit different than what's on that chart. And I should have clarified this earlier, but really we use 4.184, not just 4.18. So typically, again, 4.184, that's that constant that we can use. And then delta T, right? That's that last term right here, delta T. I went ahead and threw it in here. Some of you want to do that as a separate calculation. It's up to you. But 60.0 degrees Celsius minus 45 degrees Celsius. As a reminder, it must be TF minus TI, right? So you have to distinguish what the final and the initial temperatures are. Of course, plugging numbers in, right, it's not just the one thing you can do all at once because this has mixed and match types of calculations. This is going to be a subtraction, which has its own set of significant figure calculations, and then you have these other ones here, which again, in multiplication has its own set. So make sure you're careful about when you do the calculations here. And ultimately, when you solve for Q, that should end up being 628 joules of energy that is absorbed by the water. So that's how we quantify how much energy something absorbed, right? So we have the mass of the sample, the specific heat, which is that constant, and then we can use the change in temperature to know exactly how much energy is absorbed by the water. Number two, what is the final temperature of a 100.0 gram sample of water that has an initial temperature of 45 degrees Celsius and released 8.71 kilojoules of energy? Right, so now we're talking about releasing energy, or energy has gone away. So let's kind of break this one down. First of all, we know we're talking about energy change. Energy is being moved in and out of the sample. So let's go ahead and use that formula Q equals MCAT again. And now we have to see, again, what we're given. In this case, right, some of you can kind of see where this is headed. We have a mass. We're talking about water again, so we do have that term. We do have actually some amount of energy that's being gained or lost, so that goes there. And then you also have the delta T here, which is something that we can't really know exactly because we only have an initial temperature, right? So we sort of have this. So we got to do a little bit of work and set this up. So let's go ahead and start plugging some numbers in as much as we can. We do have this value of 8.71 kilojoules of energy, but also notice that since it is, again, about energy being lost, we actually have to make it a negative 8.71 kilojoules of energy. That's going to be equal to 100.0 grams times the 4.184 joules per gram Celsius of the specific heat of water times the final temperature. So, the delta T. So in this case, I'm going to go and write out that it is my final temperature minus my 45.0 degrees Celsius. That's my initial temperature given to me in the problem. Now, this effectively is a setup, but there's a couple of things that be careful of. Remember that this sign is important, right? Because the temperature or the energy is being given away, right? The water is losing the temperature, so that's why Q has to be negative here. And then also notice that since this is in kilojoules, right, that is different because remember this unit over here, right, they eventually all cancel off. That's in joules. So you're going to have to actually go through and account for that change. So make sure that when you solve for this, you convert between kilojoules and joules, and then you can solve for whatever you need to. At some point when you do this work, you should end up getting a value of negative 20.8 joules is equal to, that's not right. Negative 20.8 degrees Celsius is equal to TF minus 45.0 degrees Celsius. And then solving for the final temperature here, it's pretty simple math. You can see that my answer key is wrong, so that, again, is somehow left over. But that should be a value of 24.2 degrees Celsius as a final answer. So once again, it's important that you keep track of the values and knowing how they're applied, just like any other problem. And of course, the actual trick here is to make sure you remember about Q and make sure that you remember that the kilo is something you have to also address. Finally, I'm going to leave you this real-world example. A lot of times you'll hear climate scientists, or at least you'll hear the news about climate scientists, that say that global irreversible change will occur if the oceans warm by a mere 1 or 2 degrees Celsius from whatever it is that humans do. Well, I think for most of us, 1 or 2 degrees Celsius doesn't seem like a whole lot, but I'm kind of asking you to consider this. Why does that actually matter? I mean, 1 or 2 degrees Celsius is such a small amount. But don't forget, right, what exactly does that mean? Is that Q equals to MC delta T, right? Think about what values, what scale we have here for the amounts that are plugged into this formula, and then see what that means about Q, how much energy is really being added to your system. All right, so that about wraps up energy.